Problem came up in the lab once, and it's a good one. So we have a battery, resistor, capacitor. Immediately after the batteries connect to the circuit, the current in the circuit is 3 amps. What is the current in the circuit after one time constant? So if you know like the shortcut, this is like one calculation. It'll take you 2 seconds. But if you don't know the shortcut, you have to kind of do it the long way, the way you're supposed to, really. And I'm going to show you that way, and then I'm going to show you the shortcut and how it's not that bad once you know the shortcut. So immediately after, so actually I don't know why I'm rereading it. A time constant. The time constant is the time it takes for your capacitor to be 63% charged. So, you know, this capacitor, eventually I just dropped my cap, but this capacitor, over time, it's going to get fully charged, right? It's going to have 10 volts because no more current's going to go through this thing. So it's going to have 10 volts voltage, and it's going to be fully charged. Like, it'll have the most amount of charge. After one time constant, right? So after one time constant of being connected, it's going to have 63% of that final charge. The time constant ends up equaling the equivalent resistance R times the equivalent capacitance C. If you take AP Physics C, you're going to see where this equation comes from. But, excuse me, if you're in AP Physics 2, this equation is not too bad to conceptualize. Because if you think about it, if you make the resistance in your circuit bigger, the initial current is going to be less. So it's going to take more time, right? If you start with less current, it's going to take more time to charge all the way up to 63%. And the same thing with like your capacitance, right? If you make your capacitance bigger, it's going to be able to hold more charge. So it's going to take more time to get to that 63% mark because it's just going to be able to hold way more charge. So that's the equation. And I'll just write like, I don't know, 63% like charge or whatever. I don't know. So to start this problem, you know, it's kind of like, you know, you're not given much. One thing you could do is just loop rule, right? You can always do any circuit problem with loop rule. Even if this is like a, you know, just a resistor problem, you can use loop rule. Capacitor problem, you can use loop rule. Let's use our loop rule here. So the battery voltage minus the resistor drop, and then minus whatever the voltage is here. I'll say VC, right? So whatever the voltage across the capacitor is, it's all going to equal 0. Okay, so now let's plug in numbers. 10 volts for the battery minus the voltage drop is just going to be the current. So whatever the current is at a certain time, so I'll say I times the resistance minus whatever the capacitance voltage is. It's going to all equal 0. So we don't know the resistance of the circuit, but the nice thing they tell us is that immediately after the battery is connected, the current is 3 amps. Immediately after the battery is connected, the voltage of the capacitor is equal to 0, right? Because it doesn't have any charge. You can treat it like a wire. So this VC thing, you know, it cancels to 0 initially, right? So I'll say I initial, and then you can just do 10 volts minus, you know, I times R equals 0. 10 volts is going to equal, I'm going to add it to both sides, and the I initial, sorry, 3. I'm going to make it 6 because the problem initially was 6. And I'm doing that because this was actually a lab problem. Actually, let's just do 3. I'll do 6. It's too late now. 6 amps times R, you get R is equal to 5/3 ohms. I keep things in fractions. I know some teachers don't like it. Some physics teachers don't like it, but whatever. 5/3 ohms. So now we know the resistance, which is nice because we can take this equation again, and now I can do it for kind of any time. So I times 5/3 ohms minus V capacitance is equal to 0. So the V capacitance, right, the voltage across the capacitance, you can remember C equals QV, right? So I can solve for V, and I get V is equal to Q over C. So I just multiply both sides by V divided by C. You get V is equal to Q over C. So I can say 10 volts minus 5/3 I, and I'll drop the units. Yeah, I'll just drop the units. So it's 5/3 ohms times I minus Q. Actually, no, I'll just leave it as IR. I don't like when there's no units. I'll just leave it as IR and then I'll substitute it in at the end. Q over C. Now, Q, what is the Q on the charge? Well, the Q on the charge is going to be 63% of the maximum Q. So I'm going to actually say like 0.63 Q max. Okay, so 0.63 Q max over C. This stinks because I don't know what the capacitance is. Like it's unknown, but I remember capacitance is just the ratio. So this expression is really saying the capacitance is equal to Q at a certain time over V at a certain time. So if I think about the graph that this unit keeps on, obsessing over, Q, V, right? So the slope is capacitance. So at a certain max voltage, right, this thing is going to reach 10 volts eventually. It's going to have that Q max. I don't know what the Q max is, but that's fine because I can actually just put here, instead of C, I could write Q max divided by V max, which is really 10 volts. So I'll leave the graph, it's fine. So now you kind of have to do some like fraction stuff because you're putting the 10 volts on top, Q max on bottom. You get 10 volts minus I times R minus, so 10 volts on top. So 10 times 0.63, that's just 6.3 volts. Excuse me. And then you get Q max over Q max. The Q max drops out. That's pretty nice, right? Q max drops out. I don't even need to know what the Q max is, what the maximum amount of charge it's going to be. So 10 volts minus 6.3 volts, you get 3.7 volts minus IR is an equal 0. And now this is just really a piece of cake because I can have it I times, now the resistance is 5/3 ohms, and 5/3 ohms, I'm going to use my calculator. 3.7 times 3 divided by 5, you get the current after one time constant, right, because that's what we're doing, is equal to 2.22 amps. So there you go. What is a shortcut now, right? This is not like doing this, that's not something you'll see instantly, right? To be like, okay, wait, I don't know the voltage capacitance, I can put 0.3 Q max over C, and then I can take C, plug it in for those maximum values of Q max over 10, right? Like this is not like something you'll you'll see instantly and be able to do. That you kind of have to think about this. The shortcut is really if you took 6 amps over 2.2 amps, you would always get, so if I did 6 divided by 2.22, wait, sorry, I should really do 2.22 amps over 6 amps. It's going to equal, if you do it, it's going to equal 0.37, right? And, maybe you could think about that because it's like, okay, we have a 3.7 here, so maybe that's where the 0.37 is coming from. But, no matter what this current, so if this was 9 volts, right? If I did this whole step for 9 amps, sorry. And if the current initially was 9 amps and I did this whole procedure again, I wouldn't get 2.22, I would get some different number. But if I took that new result over 9, I would still get 0.37. I could make this voltage 12 volts, right? I would still get 0.37, no matter what. Obviously, I won't get 2.22 each time, but depending on the numbers, it's always going to net out to a ratio of 0.37. So, really, if you think about this, if this was our I that we're solving for, our current at a certain time, that's why I'm using a lowercase I, and this was our I initial, and I manipulated this, right, multiply I initial to both sides, I get the current after one time constant is always equal to 0.37 I initial. Now, you could just blind trust me, right? If you get a problem like this, just take your initial current, multiply by 0.37, which, by the way, 0.37, that's just 1 minus 0.63. So hopefully, it's not some random number. It comes from that time constant number. My challenge for you, if you're watching this and care about this stuff, mathematically prove, using either like Kirchhoff's law, right, and set the voltage to like something random. Prove, or like what I'm saying is like, don't set it to something random. I mean, show that no matter what your voltage is, no matter what the resistance is, no matter what the capacitance is, show with Kirchhoff's law, or show with if you're in physics C, the derivation of the charge on a capacitor as a function of time using like the differential equation. Prove to me that no matter what your initial EMF, VR, VC, no matter what that is, it's always going to equal the current after one time constant is always going to be 37% of the initial circuit or current. Because this is not a proof. This is what I did right here is not a proof. This is just an observation. If you took 2.22 over 6 amps, you get 0.37. So I try to make a general physics equation. But prove to me, if you want, and to, better your own learning, prove to me that this is the case. All right, thank you.